So this presentation is part of the series of webinars organized by DigiPro. And the topic will be semantic interoperability to solve industrial challenges in the OntoTrans project. So my name is Sylvain Gouttebroze. So I've been working at SINTEF now for a little bit over 15 years. My main background, it's about material modeling applied for the processing of different materials. I've worked for silicon, both metallurgy and PV. I worked for aluminum and ferrosilicon and also steel. But more recently, I started to work on databases, data management and data analysis, and also to try to see that in the perspective of interoperability. So what I will present you here, that's mostly the results of one new project that is still ongoing. So there is 18 months left in that project. And we'll try to give you a bit an overview of that project and the outcomes that could be interesting for the Norwegian industry. So the starting point is, try to summarize it in a small cartoon, is that you have a person that needs the data and asks for the data, and there is someone that has the data that is in a file, and then the person struggle a little bit to see how they can use this file, and then they refer to a complex documentation of the file and how you process it, and then it becomes complicated. And that's actually, if you want to summarize actually the current situation, is that usually when you will generate data, so the person generating the data says that, okay, I have, for example, material to characterize, and I will do that characterization. And in a way, your work stopped there. So in that case, for example, if you take the example that I tried to mark in blue, you will get measurement of the material composition. That's fine. Then you need to transfer data because this data is generated for certain use. So other people will use that. So, and it's not necessarily straightforward to transfer the data. So in our example there, the material composition is provided in an Excel file with a specific non-standard format. It's just the person that made the measurement or decided on a format. So the person receiving it need to understand that format and be able to extract information. So that's the first step, is kind of how you transfer the information by format. The second step is that you need to interpret the data, because you need to understand how this data was generated. And usually then you need a direct communication with the data owner, for the person that generated the data. So for example, a very classical case. So in this characterization of the composition, you have a name for the sample. But where this name comes from? Is it the same name that the person, let's say, making the casting, for example, used? And you have also a question about if this Excel file contained the units or different variables. What method was used, because it might matter. So for example, you might have some high uncertainty on specific elements because of the method that was used. So all this information need also to be present somewhere so that the person receiving the data can use it properly. And what's also important to see is that now more and more you have multidisciplinary research and complex projects that will require large and frequent exchange of data. So it means that what we started, it was just an independent act about measuring a property. It needs to be combined with other information. So in a case, for example, you need to combine the composition data with the temperature measured in the furnace during the process. And maybe you want to execute a model that will compute the properties of the material after that process. It might include also calibration with previous test measurements. So you see that you need to combine usually a lot of data that are coming from different sources. And this is challenging. So question is, how do we improve that situation? So the first thing is that, as I tried to mention before, that we need to document the data. We'll see later what it means by documenting the data. And how can then we facilitate the reuse of this data, both new data that we generate now, but also historical data that was generated 5–10 years ago. And there, the recommendation is to use a data model to represent our data. And finally, how do I explain what my data is, what my variable means? Then we add semantic description to that. So that's a bit how we should ideally do the work. But then in that perspective, what OntoTrans project deliver that could help solve this issue? So if we look quickly at the objectives of the OntoTrans project, so it's about semantics translation scheme. So that's a bit complex phrasing, so I will try to explain you a little bit later what it means. But the starting point is that, and it's very important, you want to start with an evaluation case. So it means that you have a company that has an issue and they need to solve that challenge. And in OntoTrans, that's focused on materials. So they want to convert an innovation case to something about material modeling. And what's important there also is that OntoTrans based kind of all this framework on the fact that you will have a description that is based on ontologies. And for this process, you will need also a lot of interaction between different environments, different actors. And the final part is that the work on OntoTrans is directed toward industrial environment. So it means that the tools that are developed there should not stay in academia. They should be usable also by industry. So a few words about the consortium, and it's just to show the partner of that project. And you have a mix of research institutes, universities, consulting companies, very large companies like ArcelorMittal and Procter & Gamble. And you see that you have a variety of material that is considered here. You have ArcelorMittal that's more on steel, then Procter & Gamble it's most on laundry products, and you have also composites. And you have also companies that are dedicated to data analysis. So basically data storage and CMCM. So this consortium is built to raise, in a way, the challenge defined by the EU. And you see that if you look at the consortium competencies, it's very broad. And we'll see why we need all these type of competencies. But the name itself, so OntoTrans, it stands for Ontology-Driven Open Translation Environment. And it's not obvious what it means now. So I will try to explain you quickly the main concepts there. So ontology, translation, and open translation environment. And after that, after introducing this concept, I will try to present the tools that have been developed to facilitate this work and provide some example. I try to illustrate how this piece of code can help and be used. So the main concepts. First, an ontology. So an ontology, that's by definition the concepts and the interrelation for domain of interest. And it's based on logic. So this is very important because it enables a lot of processing of the knowledge. And also what's important is that it's formalized. So it means that a machine is able to understand that. So what do we mean by concepts and interrelations? If we look at the word, so we have real objects on the right. And humans will try to conceptualize that to facilitate the manipulation of the subject and think about those objects, how they should be represented, what we can do with them. And the role of the ontology is to, in a way, write down this conceptualization into a certain format. And as mentioned before, what's very important is that this format is also understandable by machines. So it means that you can handle very large number of concepts and try to reproduce part of the reasoning that takes place in the human brain. So here it's a short example about, in practice, what it means to build an ontology. So here, that's an example taken from the elementary multi-perspective material ontology. So that's ontology developed mainly in Europe to describe materials. And so the core concept is, of course, material. What is a material? And you have two things in this picture. So you have a set of definition, comments, and examples to explain as clearly as possible what the material is, so that everyone that get, okay, this data represent material, then you can go back and see the definition. And what's really important also, it's that you have relations. So this material is actually made of matter that is related to all the concepts that are grouped in the physicalistic concept. And this material can be different things. So it can be a chemical material, it can be a crystalline material, it can be a nanomaterial, manufactured material, reactive material, natural material. And attached to this concept are other sub-concepts. So for example, for here, then you need to define what is a crystal. And step by step like this, you build knowledge that describe what you already know in a way about your process, about your domain. But the important thing is that you have written down clear definitions and clear relations so that it can be processed later and communicate to others also. Because one important aspect also in this ontology is that usually it's open, so everyone can access it. So no, the second concept was translation. And translation in that domain does not mean converting from one language to another. It started all by the statement from the EU that material modeling is a key enabler for innovation. And they found out that it's underused. So in a way, they asked for a project that can help solve that issue. And that's why this project, this EMC CSA, so this stands for European Material Modeling Council, started. And they defined the concept of translation for material modeling. It was a strong effort linking many different industry, academy, and research institute. So the aim of the translation, so it's that industrial user can benefit from the development in material modeling. And how is that done? It's that by having a methodology to translate industrial challenges into a solution. And this solution is based on combining material modeling and simulation tools. So let's see a simple example. So we start with an industrial problem. This is translated into, let's say, a subset of problems that can be solved by a model, where you can get values out of the simulation. And the simulation might be a complex one. So usually you end up with different steps. So you start with some input, and then you will perform some computation, start with output. This output must be processed so it's understandable, and sent to another model. And like this, you get some information about the process. And an important step is that this result from the simulation then will need to be interpreted. So you have an interaction between the person doing the modeling and the person needed to solve an industrial problem. So the translation, it's this iterative loop where it's very important to have good communication between the customer and relate his challenges to business decision that is supported by material modeling. So that's a bit the concept of translation. So this is a complex situation, and as pointed out already, it needs very good communication. It needs also transfer of data, because you have transfer of data both from the company, the different models that are involved, of course, experimental measurements, and important aspect also is that you need to be able to integrate the most recent tools, because that's what you want, but use the most up-to-date solution. So you need to facilitate the integration of the modeling tools. And what's also very important is that you want to reuse the same method. and the same tools for new challenges that arise in your company. So that's why it seems very important to have an open translation environment. So meaning an environment that helps you doing all this work. And that's what OntoTrans is all about. So in OntoTrans, there are different layers of information. So you have the user on the top that come up with the requests, and then they want to solve their problem. And then the translator will need to, in a way, explain, oh, you can solve that problem with certain modeling workflows, certain experiments, and this kind of this. And the end user will not usually directly interact with the very advanced models. That's why you have, for example, a wizard. So that's kind of an interface that will help you enter your specification more easily in a way that you understand. And then it's connected this layer to interact with the modeling tools or any other tools. And what's important here is that you have an aspect where you store the knowledge, learn from previous simulation, previous work, what you already know, and this is stored in a database. And the goal also to OntoTrans is to build a recommendation system that will tell you, okay, this is this type of problem that I'm trying to solve, and I have already in my database that this approach has been used to solve this problem. So maybe you want to try that one. But for the presentation today, what's really important is this OntoTrans API, the one that enables the connection between all these components. And it has two main parts. So the first one is the OTEAPI. So that's a framework for accessing data resources and perform data transformation. That could be computation, that could be pre-processing, that could be plotting, that could be anything. The second part is DLite, and that's lightweight data center framework for semantic interoperability. So now we try to enter the core scientific part, if I want to say. So semantic interoperability, I will try to explain you what it means and to illustrate two key aspects of its data models and pipelines. So, but we're back to, if you remember the introduction, that to be efficient in your work, you need to document your data. That's really important, so that you are able to communicate data that is useful for others, that can be useful also in the future, that you can reuse and process easily. And when you look at data documentation, so this is a set of description, so formal and informal, that gives context to the data in order to facilitate, as I said, findability, reusability, and interoperability. So it's kind of a lot of different information that should be added to the data. And what's really important is that you need to have separation between the different roles of the people involved in that interaction with that data. So you have, of course, the first one that is the data provider that will give access to the data and that will do this first metadata documentation. You have then the modeling tool provider that needs to implement in a way wrappers to be able to ingest the data that will be provided. And then you have the role of the curator that need to make sure that the data that has been generated is stored properly and is findable. And then you have the ontologies that come in between, if I can say, and they try to formalize the knowledge and formalize that if you describe your variable as this is related to a concept that is agreed upon in the community, so that everyone will understand your definition. So the semantic interoperability, it's all about the ability of computer to exchange data. And the most important aspect when you exchange data is that it has to be unambiguous and with a shared meaning. In addition, when you start to implement semantic interoperability, you unlock new possibilities. So to apply logic, reasoning on your data, possibly also discovery of information that is actually stored in your knowledge graph, but it's difficult to extract without that. And for what is important for us, it's also facilitate a lot the communication between systems and users. And to achieve semantic interoperability, you need to have a semantic description, and that has to be based on an ontology. And the second point, to really realize that, you need a framework so that you're able to actually share the data, not just putting in place all the tools, but really use it. So when you, so your aim is, of course, to simplify the sharing of the data. That was a starting point, and that's kind of the most important part here. And the semantic interoperability will allow you to hide the complexity of the interoperability operation. So it means that if your data is properly described, then it stops there. You don't need to specify that my data in certain format, or I want that data in certain format. No. Just need to specify that's what I want. I want, for example, a material composition. That's what you will get. Whatever the format of the initial provider has put, if he has done his work properly in a way, and it's semantically described, then that's all you need to know. What's also important is that it helps communicate unambiguous information. So it kind of enforces you to remember what is essential for the communication. So for example, if you communicate the value, it will not be accepted if you don't have specified a unit. And in addition, your value is associated to a concept. So for example, a concept of temperature. So if you put value in second, it will fail. It will not be accepted because temperature cannot be measured in seconds. So it has to be usually Kelvin, Faraday, Celsius, whatever, but it's limited. So it's kind of help you also to deliver consistent data. And of course, as we said, it improves reusability, discovery, accessibility. So no, the thing is that we are not working with one data set here and there. We are working with multiple sources of data and often large amount of data. So it requires some standardization and some automation. And that will be the two main points that I will try to present next. So the standardization, it will be done through a data model. The automation, it will be done by execution of workflows. Okay, so here the first part is data models. And the data model I will present now are based on the DLite choice of representation. So the first thing is that this is the ontology that describe a data model for DLite. So you have an entity, specify some dimensions, there's an identity, then you have a shape, then you have different properties that have to be defined with a label, a unit, a description, and a type. So that's it. That's what data model needs to contain. With this constraint, then you can build a real data model that is supposed to describe a real data set. So here we made it very simple in the example. So it just, as before, a composition. So we get that we need a property that lists the elements that enter the array. We need them composition that will be the amount in a certain unit, in that case, atom fraction. And you see that we add a variable dimension, and we see that we enforce that these two arrays have exactly the same size. Otherwise, this will not be a valid representation of our data. And you have an addition, for example, an additional property, for example, density. So this description that's kind of done manually is then converted into a human readable file like this. So you refer first that, okay, this is my new data model. There is a description, then there is a number, and then you have all this. So include, as we said, what is mandatory, a type, a shape, a description. The unit is not completely mandatory. So because then we just assume that there is no unit, and for a string, that's fine. So okay, so now we have defined our data model to represent this array. What we can do now is that create an instance, so real array, then we have measured the composition, and then it will end up like this. So what it says is that it is of this type. It's using this scheme as a data model. And then in our case, it has dimension 4, because we have measured only 4 elements. And then you have the value, and then you have the density. So that's, in a way, this approach to data model. It's a way to systematize the way you store your data, and you enforce that you have some description that are in place. So now the second part, it's about workflow. So how you want to facilitate your interoperability by enabling something that is called the pipeline. So pipeline, it's a chain of processing elements and configuration. The output of one element is the input of the next. So it's kind of, you have successive operations, basically. And you have different type of elements that you can put in this OTEAPI pipeline. So you have data resource. It just represents something, a database, a file, whatever. Then you have a filter that will define a subset of that data resource. And then you can do an important step that is called the mapping. So we have seen previously, so for example, if we take that data model, so we have some variables here. That's fine. But remember, we don't know actually the meaning of elements. We don't know the meaning of composition because this is just a string in a way. So the important role of this mapping here is that you say that when I'm saying elements, it corresponds to a list of chemical elements. And then everyone is supposed to understand. When you have done that, so you have added a semantic description of your data. And you can perform two types of operation. What is called a function. So this is a synchronous operation. So it means that the workflow will not go further until this operation is completed. And it's supposed to run on the same server, for example. And you have transformation that is more time consuming. Then it's something that you launch, for example, a simulation. And then from your workflow will continue only when this transformation is finished. So this is, for example, a connection to a supercomputer or something like that. Okay. So now all these two things are connected together. It's that you start from the left because this is what you want. You would like to run a simulation. That's fine, but you need to get data. And you know that this data is in a database. It has been, the material has been characterized. That's good. So we know that, okay, you can access this data here. So you have a step where you parse this data. So it means that you convert in a way the internal representation format to something that will be useful for your workflow. You map all the information that has been extracted from that file or that database into your knowledge graph. So you connect all the variables to concept that has been defined in your ontology. So for example, this variable T is actually temperature. On the other side, so you know what your model needs. So you define what it needs. So for example, in that example here, it doesn't need a picture of the grain orientation. It needs this. That's ODF graph. So that's what you said. You said, this is what I need. And then you have defined all the concept connected to the database again. And what's important is that the pipeline will go one way. It will go first in the initialization in that direction. So from the transform, it will define the map, transform, map, parse, and source. And when you will execute, then it will go the other way around. So it means that the information provided here about what you need will be transferred in the initialization step to this part here. So this part will know that what you expect and then decide how to convert this into this. Okay. So now there are two ways, in a way, to two classical things that you do with your pipeline. The first one is that you have some data and you want to store that information in your knowledge base to be reused. And so you define a data model, a mapping, and then you need a reader or parser. And you will execute that. And so you store your information. The second type of interaction is the opposite. So you want to fetch something from your knowledge base to be used for your simulation or business process. And then you start with the mapping, of course, because we need to know what you want, what you need for that software. And then you associate to it the data model, and then it goes that. What's important is that all this here in the center, it's semantically described. So it means that it can interact with many different pipes. And these pipes can also be combined directly. So that's kind of quite powerful. So now we'll try to finish with some application examples. 2 examples from the OntoTrans project, steel beam manufacturing and composite processing. So the first case. So this is the process of forming steel beam. So they start, of course, with molten steel, and then they have different steps. So in the first 6 months of the project, then there was a discussion between, let's say, the core OntoTrans team and the distributor partner to define these different steps here. And when you start to define that, so you start to also at the same time think about how they should be described in the data model, and do we have a clear definition about what we mean? And that's why they started to build this ontology that describes this specific case. So it means that this ontology is also supposed to be connected to a kind of top-level ontology that describes the main feature, the main physical phenomena, the main things that are observed. And then this becomes kind of a children of that main ontology. And you see that they have defined the different process steps, they have defined the paths that are involved, a lot of things. So they get kind of from a very schematic graph into something that provide in a way the same information but formalized, so that can be exploited by the rest of the tools. So when you have done that, you see that you have defined different concepts. And in addition, what we have started to find then it's a data model to represent that. So then we generate a definition so that we have from blooming duration, that's a float, that's measured in seconds, and then you have a short description. So that's the short description are part of the data model. But what's more important is that you associate to that a mapping. So it means that we say that here, this blooming duration, and you see you get URI, so that's composite between this identification of your data model extended with the name of the variable, so here. And then we say that it maps to a concept in the ontology and maps to the, so this ontology has been defined like this. So this is the name of the ontology, and then you have the concept associated to it. It means that you have direct correspondence between the data model and information stored in the ontology. But those two are separated because we might need later, for example, to provide this information to another company to change the mapping. The data will not change because the data is what has been measured. But the mapping could change because maybe that customer has different names for that concept because they use their own internal ontology. It means that it makes it quite flexible so that you separate the representation of the data and the mapping, so the concepts that are associated, the meaning associated. So now a little bit about trying to illustrate how powerful this pipeline can be. So the starting point is, of course, as we said, that we have some data source and we want to convert into another format. That's fine. That's simple to understand. At the center, we have this operation when we map from one data model to another data model. Sometimes it's very straightforward. So you have a variable called pressure and you have a variable here called current pressure. And both has been defined as pressure. So well, no conversion needed. We just say that this variable in this data model corresponds to that one. That's fine. Let's go now to a more complex case. Because you see that we have not represented the temperature in the same way. So here we have represented as initial temperature, final temperature, and the duration. So it's kind of linear evolution. And here we have called that temperature ramp. So that's slightly different. But it's fine because we can compute it. I mean, if we stand here as a human to convert that, we'll understand that this formula could be used. But we need to remember that we need to automatize also things. So we want to avoid or limit that there is a need for a strong interaction between the person delivering this data model and the person delivering this data model. But what is possible is that we have defined all our concepts in this ontology. And we can look for, in our knowledge base, a function that can actually do this conversion. And if it has been defined with this concept, so there is a duration, initial temperature, and final temperature, and its output current temp range. So it means that we are able to find in our knowledge base that, yes, there is a function here. And what's more important is that this function then is also executable, so that your pipeline can find this function here. Because the way those are defined, it finds the function and then it's replaced this kind of black box by a certain function that will be called when you execute the pipeline. And this, where it's very powerful, is that this can be automatized. So it means that if you change something here, you can look for the function that will do the conversion. So, but of course, all this interoperability, there are some challenges. So what's really important to see and understand is that the benefit of semantic interoperability will grow exponentially. So it means that the more data you have, the more you will see the benefit, because if you do an operation 100 times, then you see the benefit is automatized. If it's only really from time to time, then it's not that obvious what is the benefit. So it's why sometimes it's a bit challenging to have kind of small scale demo that are very, very convincing. So the expectations also are usually set very high about the semantic interoperability. But what's important to remember also is that it requires an infrastructure in the background so that this can be executed. And it also requires that you have formatted properly a lot of your data and that you have started to build some knowledge space. So when you can infer knowledge, so for example, as before, that you can find this function that because someone has placed it there as a needed for it before, and then it's already in your knowledge space, and then you can find it again. What's also important to remember is that the definition of this data model, it will go for trials and error, because you will learn step by step what is it that you want to express and what is it that others need. And you might like iterate like this, enrich the way you describe your data, change the term because sometimes the terms are not adequate to another person, they don't understand it properly, and this kind of things. And what's really important is that the solution that you select must be flexible to follow the evolution of the data model and data processing, because we know that it will change. We know that we require more of our data. So it means that we need to be able to extend the description of our data so that it's compatible with future processes. So to summarize, in a way, this is the situation we started with, where you have a difficult exchange of data, and we hope that we'll get this solution. So here, the person is still asking for the data, but the person is answering that, okay, but this data has been stored there in a certain database. And the person is saying, okay, then I just get the URL, what am I supposed to do? And the answer is nothing. It should work out of the box. So you just specify that URL and then it enter your pipeline, and this interoperability tools will do the conversion for you and will do more than that. It will also return the result as you expect them, whatever the source. So that's very important. Yes, so I try to summarize a little bit, take home message. So of course, it's that data are valuable only if they are usable. And for that, you need to document properly your data. It's very important. The second point is that ontology is becoming more and more used, at least in our field, because it's a nice way to systematize the knowledge. and make it available to both humans and computers. Our point is that no, there exist some tools to facilitate the documentation and enable interoperability. So we don't need to start from scratch. And the final point is that this methodology is becoming mature. So it starts to be usable by other outside this kind of research project. And of course, if you are interested to know more, you would like to take this tool, you are very welcome to contact us. And I also would like to mention that we have also a project financed by the Norwegian Research Council, where we can also test some small demonstrator. So if you come up with a case, then we can try to model it. On that, I would like to thank you, and of course, thanks the support from the European Union and the Norwegian